In this video, I will talk about vibrational modes of water. Simply, I will try to find out the vibrational modes of water by using group theory. So firstly, we need to know degrees of freedom. If you don't know the meaning of degrees of freedom for the molecules, please watch that video first. As you remember, for the degrees of freedom for linear molecules, we have 3n minus 5 number of degrees of freedom. This is for linear molecules. For nonlinear molecules, we have 3n minus 6 degrees of freedom. As you know, water has a band structure. We have two hydrogen atoms and we have one central oxygen atom. If you apply this formula for the non-linear molecule, which is water, and n is the number of atoms, we have 3 times 3 minus 6, and we have 3 vibrational modes. Since these 3 of them is translational, and the other 3 of them is rotational motion. To solve this problem, firstly, I need to determine the point group of water molecule. I made a video that shows how to determine point group of a water molecule. I will show it here very briefly. We have a C2 principal axis. We don't have C2 perpendicular to our principal axis. So this is not a D group. And we have 2 sigma planes, so that our point group for water molecule is C2V. Simply, I determined the point group of water molecule. In the second step, we need to make a representation for X, Y, and Z axes for each atom in a water molecule. To make this calculation, I need to use C2V point group table. So this is our point group table, which is C2V. And I need to look at the X, Y, and Z coordinates for each atoms, and I will write a reducible representation for X, Y, Z coordinates. So we have a water molecule. I want to write a water molecule here, and we have X, Y, and Z. This is Z axis, this is X axis, and this is the Y axis. And we have all the X, Y, Z axes for each atom in the molecule. And I want to delete here. Okay. And I will write my reducible representation. So this is my reducible representation. And basically, I will look at the all motions of the atoms in the molecule in this representation. Maybe I can write this representation as X, Y, Z. So firstly, if we apply E element, or what is E element? E element is do nothing. Okay. Therefore, if we apply E operation here, I'm applying the E operation, 9 of the axes will stay at the same position. If the axis stays at the same position, I will write it as 1. If it changes, then it means that it changed and therefore it became 0. And you will see in the C2 axis operation, since we have a C2 here, that includes the z-axis, and what happens is that axes on hydrogen atoms changed. Since this hydrogen atom will come here, and the other hydrogen atom will come here. So I will not consider the axes on the hydrogen atoms. But oxygen atom stayed in the same position after applying the C2 operation, so that I have to look at the only oxygen. But I want to write the oxygen here. So we have oxygen axis. We have oxygen in the middle. Okay. And we have again X, Y, and Z components. What will happen if we apply C2 from here? Firstly, is one Z. Z will stay in the same position. So Z will become Z. But Y will go to here and it will become a minus Y since it go to the other position. So it become minus Y. And likely X will become minus X since after the C2 operation X will go here. So this will be minus X. So I will sum the coefficients on the axes. So Z have plus 1 coefficient here, of course. Y has minus 1 and X has minus 1 coefficient. So at the end I will have minus 1. I just summed all of them. So we have minus 1 here. I will apply the sigma V. We applied this one. And I will apply first sigma V, which is the XZ plane. And as you see, I will put the XZ plane here. Right? This is our XZ plane. If I apply the XZ plane, you will realize that oxygen atom stay in the same position. But we don't have to consider the hydrogen atoms since their positions again will change. And I want to show it here again, since this part is a little bit complicated. So this is our water molecule, and this is the X, this is Y, and this is the Z axis. And I will apply this plane, right? So molecule just cut it from the middle, which means that this hydrogen will go here and this hydrogen will go here. Okay, and I want to delete these arrows to make it easier. In this case, what will happen is that I will just consider the oxygen atom here. So after the operation of the sigma, which is sigma V, Y will becomes minus Y. I'm just doing the same thing here. Z will becomes plus Z, and X will becomes same, plus X. So after the operation, I will again sum them up, and it will be plus 1. Okay. And I will make the same thing for our last operation, which is sigma V YZ. I want to clean it. And the important point is that you should always use the same axis notation. Otherwise, you will make a huge mistake. So this part is important. Okay. Again, we have oxygen atoms. And I will apply the sigma YZ operation. So if we apply the sigma YZ operations, all atoms will stay in the same position. We have to consider all atoms in water molecules, since our plane just covers all the molecules. So this is simply sigma YZ. And I want to show it here. This is the plane. Of course, it is infinite. So I will draw the X, Y, Z for each of them. Okay, we have Y here, we have Z here, we have X here. So the position is important. And we have this thing here. And I can write in these positions, of course. And I will apply to sigma v for this xyz point. So I am just looking here, okay? So if I apply the sigma v, and x will become minus x, since this x will go to the other side, this is a mirror, and it will go to the other side, y will still same, y will be y or plus y, and z will become plus z. So if I sum them up, it will be plus 1. However, I have 3 of them. So I did only for this hydrogen atom. If I do the same thing, it will give the same result for oxygen, and it will give same results for the hydrogen. In this case, I have to multiply it with 3 so that it will become plus 3. And this is our reducible representation. I will write the reducible representation here to make life easy. 9 minus 1 plus 1, 3. So this is our reducible representation for oxygen, hydrogen atoms in the water molecule. So here I just want to talk a little bit about how to find combination of our reducible representation. So this is important. And firstly, we have to know a few things. First thing is group order. Group order is simply summation of all coefficients of the symmetry operations. As you see, we have the symmetry operations here, and I will just sum symmetry operations to find H. And H is also called as group order. This is an extra information, but it is fine, I think. E has, so here E has 1 coefficient, C2 has 1 coefficient, sigma V's has 1 plus 1. We have 2 sigma V, and their coefficients are also 1 here, okay? So the total of H, or the order of this point group, is 4. So I want to write a very simple formula. Formula to find the combination of reducible representation is just our number. For instance, our number for E element is 1. No, is 9. Okay, this is our number. I'm just calling this thing as our number, times irreducible representation, one of the irreducible representation. For instance, 1 is one of the irreducible representation. So I'm just looking at this part. It's important. And I should write it irreducible representation. I will use abbreviation. And coefficient on the symmetry operation. Coefficient on symmetry operation over H. And in our case, H is equal to 4. So I make this part very small since I will need this area, but you can look at to use it. Maybe it will become very small, but you will understand in a minute. So the answer is, for instance, how many A1 irreducible representations in our reducible representation, and our reducible representation is this one. These are the irreducible representation. All of these are irreducible representations. So I am wondering how many A1 is in our reducible representation. Firstly, I have to divide by 4. 1 over 4. This is the 1 over 4. I will apply this formula, this part, for E, then C2, then CVs. Okay. And I will write it 9 times 1. I'm looking at the A1 and coefficient on the E. So 9, 1, 1. I hope you understood. 9, 1, 1. So I wrote 9, 1, 1, which means that I will always go from bottom to top. This is very important since making mistake is very, very easy. This is the most important part of our calculation. Times or plus, I will make the same thing for the C2 operation, minus 1, since we have a minus 1 here, this is minus 1, times 1, I will go to the operation number on the A1 for C2, which is 1, and C2 coefficient is also 1. Then I will make the same thing, plus 1, plus 1, plus 1, plus 1. I will make the same thing for this one, 3, 1, 1. And we can make the calculations. This is 1, this is minus 1, this is plus 1, and this is plus 3. These two will cancel each other. 12 over 4 equals to 3. So we have 3A1. Okay, 3A1. I will write here. And I will clean this part. So this is 3, and this is plus 3. And I am wondering how many A2 in our reducible representation. Again, this is our reducible representation. I will do the same thing from bottom to top. 9. Right now I am looking at the A2, which is 1, and coefficient on the operation is 1. So 1 over 4, I will always write the 1 over 4, since 4 is always here, times 9, 1, 1, plus minus 1, 1, 1, plus 1, minus 1, 1. Plus 3, minus 1, 1. I will calculate it. This is 4, this is minus 1, not 4, this is 9. My goodness, this is 9. Minus 1, minus 1, and minus 3. So in this case it will be 4. 4 over 4 will be equal to 1. In this case we have only 1 A2. Okay. Then I will look at how many B1 here. So this is just will be a number between 0 to something, an integer. 1 over 4, and I should clean here. So 9 1 over 4 times 9. 9 will always be here since it is our reducible representation. 1 from B1, since I'm just looking at the B1. Then the coefficient of the E, 1, minus 1, again minus 1, and plus 1. 1, 1, 1. And plus 3, minus 1, 1. So I will calculate it. This is plus 1, this is 9, this is 1, this is minus 2. It will become 8. 8 over 4 equals to 2. So this is B1. And I will apply the same thing for B2. And I want to use alpha here. Okay, alpha. B2. Again, same thing, 1 over 4. I want to clean here. So B2, for B2, it will be 9. I'm just using 9 here. 1, 1. Then minus 1, minus 1, and 1. Plus 1 from our representation, and minus 1, minus 1, and 1 from here. Then plus 1 or plus 3, first our representation, plus 1, or 1, 1. And it should be equal 12 over 4, so it is equal to 3. So I didn't write 2 here, maybe I should write 2b1. Okay, and we have 3b2. If you add them up, you will find that our representation is this. So we can write reducible representations by using irreducible representations. But this is simply 3n. So this is 3n, right? Since we made our reducible representations by using the 3 axes. So this is the 3 axes, x, y, z, and n is the number of atoms. Therefore, if we don't do anything, it becomes 9. I guess you understood. I will not talk more than it. And we can continue to solve our problem, since our main aim is to find the vibrational modes. So what is our vibrational modes? Firstly, we have rotational and we have translational motions, and we can understand them by looking at the point group table. I want to clean here, since this is just a calculation. And this is our representation, which is very important. This is not important, since I know my representation right now. Okay, so this is our representation. And this is equal to r, x, y, z. Okay, so again we have a rotational motions, and the rotational motions are represented by r. So these are our rotational motions. So I will remove the rotational motions which are minus b2, minus b1, and the other is a2. I will just sum them up, and I will get rid of from the rotational motions. We have also translationals. And translational motions are represented as, I will use red color, X, Y, and Z. So simply we have to subtract the A1, we have to subtract the B1, and we have to subtract the B2. So we will cancel one of the B2, one B2, so 3B2 minus 2B2 will be 1B2. B1 completely cancel, right? We don't have B1, sorry. And A2 will also cancel, and we will have 2A1, since A1s will also cancel each other. So this is the vibrational modes of water. Vibrational modes of water are 2A1 plus B2. So we expect to see 3 vibrational motions. Is it reasonable? The answer is yes, since if you apply the 3 and minus 6, n is 3, minus 6 is equal to 3. So we have 3 vibrational modes. To understand whether it is Raman active or infrared active, then we have to look at our point group table. So we will look at whether A1 is Raman active or not, and we will look at the B2 whether it is Raman active or not. So for A1, we will look at the quadratic and linear functions. If there is something on the linear functions like Z, then it is IR active. A1 is IR active and B2 also IR active. So we expect to see 3 IR peaks of water molecule in the infrared spectroscopy. Is it Raman active? To understand whether it is Raman active or not, then we should look at the quadratic functions here. And we can see that A1 and B2 are also Raman active. And this is it for me. I hope this course or this problem solving became very useful for you.